Hey, I'm glad to congratulate all the participants of the conference, and I would like to present research on the topic Modeling and AI-driven adaptive learning platform for students with special educational needs. Authors Ihor, Chushchak and Vasyl Andrunyk. The need of equitable, high-quality education has spurred the rise of digital platforms that use generative AI to create, personalize, and refine learning experiences. This technological shift aligns with global initiatives to promote social inclusion and to comply with international standards on accessibility and equal rights in education. The exigency of addressing diverse learners' requirements, spanning cognitive and sensory supports to highly adaptive instructional methodologies, drive the need for robust, meticulously modeled information systems. From a system engineering perspective, designing an educational platform for learners with special educational needs involves managing multiple layers of complexity. Adaptive learning is an innovative educational approach that leverages technology to personalize instructional materials and methods according to the individual needs of each learner. This approach has gained particular relevance in the field of inclusive education, where students with special educational needs require tailored support that addresses their cognitive, emotional, and sensory characteristics. Thanks to recent advancements in artificial intelligence, it is now possible to design adaptive platforms capable of dynamically adjusting educational content in real time. These intelligent systems analyze diagnostic data, track student performance, and respond to behavioral changes, ensuring that learning pathways remain relevant and effective. In Ukraine, there is a growing recognition of the need to update educational environments to better serve students with disabilities. The integration of AI-powered adaptive learning platforms marks a significant step towards providing high-quality, individualized education for all students, regardless of their specific challenges. The goal of this work is to model an AI-powered adaptive learning platform that provides individualized instruction for students with special educational needs. The platform must continuously process the four key streams of information: diagnostic data that outlines the learner's cognitive and psychophysiological profile, contextual information such as classroom environment and available support, the student's current educational goals, and real-time feedback on engagement and performance. Together, these elements form a comprehensive snapshot of the learner's state. Based on this snapshot, the platform must then select the most appropriate action from a set of AI capabilities, including content simplification, multimodal media generation, task sequencing, and real-time alerts. The chosen action must advance the learner's educational objectives while adapting to their specific conditions and context. Each decision is followed by system-level feedback, evaluating learning outcomes, emotional engagement, and psychosocial well-being. This feedback is essential for updating the platform's decision-making policy, ensuring that future actions generate greater value. The core challenge, therefore, lies in designing a system that can continuously learn and refine its policy for mapping complex and variable learner data to effective strategies, promoting long-term progress. This slide presents the use case diagram, which illustrates the full range of interactions between users and the AI-driven learning platform. The diagram formally defines the permissible sequences of actions that take place within the boundaries of the modeled education environment. Each actor in the system, including student, parents, teachers, institutional administrators, and AI agents, interacts with the platform by contributing to or receiving outputs from a series of processes. These processes include psychophysiological testing, pedagogical diagnostics, and development of personalized learning objectives, and the creation of individual learning plans. The platform integrates data from multiple stakeholders to assess progress, personalize resources, and continuously refine educational strategies. Notably, it also features feedback loops such as analysis of AI assistant performance and learning outcomes, which help improve decision making and overall effectiveness of the learning environment. This diagram represents the UML activity model, which outlines the step-by-step adaptive learning workflow for a student with special educational needs. The process begins with the acquisition of initial psychophysiological assessment results, which are then used to survey stakeholders and generate a comprehensive digital profile of the student. Following this, adaptive AI agent is configured and begins generating personalized recommendations. These outputs inform the update of the student's individual learning trajectory. During the learning session, digital support is provided in real time, while formative assessment results are collected to track progress. Post-session analysis involves identifying specific changes in communication, social behavior, and academic achievement. These observations are aggregated into a central analytical repository. The system uses this repository to refine its recommendation algorithm, ensuring continuous improvement. This slide presents a formalized model of the inclusive educational process for individuals with educational needs, using the mathematical abstraction of Petri nets. During the analysis of the educational workflow, several core functional stages were identified. These stages are characterized by structured sequences and the need for synchronously executed tasks. To model this complexity, we apply the Petri net formalism, which enables both graphical and analytical representations of processes. The Petri net is defined by sets of places and transitions, which correspond respectively to conditions or states, and to actors or events that trigger changes within the system. This approach allows for the clear mapping of dependencies and the timing of instructional activities. In this model, transitions denote the achievement of specific educational objectives, while places represent the necessary preconditions for these objectives to be fulfilled. Figure 3 illustrates the Petri net modeling the learning path as a system of interconnected steps that collectively support the personalized development of students with special needs. This slide presents comparative performance analysis between a traditional learning management system and the AI-driven adaptive platform. This consolidated dashboard synthesizes key educational indicators, highlighting how AI integrations transforms learning outcomes. First, we observe an increase in the mean post-test score from 71% to 80%. This improvement is attributed to the platform's ability to dynamically adapt content to each learner's knowledge gaps, thereby enhancing comprehension and retention. Second, course completion rates rises significantly, from 70 to 90%. Adaptive learning pathways combined with real-time feedback help students stay motivated and on a track with clearly defined, achievable objectives. Finally, the average daily on-task engagement increases from 32 to 41 minutes. This is driven by personalized prompts and interactive content that maintain student focus and encouraging active participation. Together, these results underscore the effectiveness of AI adaptive platform in promoting higher learning efficiency, engagement, and retention compared to conventional systems. This slide builds upon the comparative data presented earlier, confirming that AI adaptive learning platform outperforms the traditional LMS across all observed dimensions. To quantify how real-time personalization contributes to learning success, a multiple linear regression model was constructed. The equation models post-intervention performance based on pre-test scores, adaptability of the AI system, and daily engagement minutes. The regression results confirm that each of these variables has a statistically significant effect. The adaptability coefficient is particularly strong, suggesting that AI platforms' ability to personalize instructions is the most influential factor in boosting learning outcomes. In conclusion, this study confirms that developing an inclusive educational information system driven by an integrated AI assistant marks a significant step forward in delivering equitable, high-quality learning experience for students with special educational needs. The proposed framework integrates regulatory compliance, adaptive pedagogy, and cutting-edge technologies such as generative AI, reinforcement learning, cloud infrastructure, and privacy-preserving analytics. Through this model, educational pathways become fully personalized, continuously adapting in real time to diagnostic data, learner context, and ongoing performance feedback. By embedding these capabilities with a reinforcement learning paradigm, the system not only addresses immediate student needs but also evolves intelligently, aligning instructional strategies with individual learning profiles. Ultimately, this work presents a scalable and resilient foundation for future digital learning ecosystems. Systems that are inclusive by design and personalized by function, ensuring no learner is left behind in the digital educational landscape. Finally, thank you very much for your attention.